Uh, so hi, my name is Kayhan. Our work is on Gaussian graphical models, and we have a new algorithm for solving these problems. So in Gaussian graphical models, we are given n data points from a normal distribution. And we know that the precision matrix of this distribution is sparse. It doesn't have many non-zeros. What this means is that the graph of this network is going to be sparse. There aren't many connections over here. And what we're interested in is trying to estimate this matrix from the data that we have. So what we do, we introduce a new framework based on the pseudo-likelihood notion. And we provide a new formulation for this problem, which is based on this L0 type regularization to induce the sparsity. And the results that we have are, first, we show that statistically, what we have is we have estimation and support recovery guarantees. And what we can show is that our guarantees are minimax optimal, and they are better than, they're as good as or better than current guarantees that there are for this problem. And if I can go to the next slide. So also, we have a specialized algorithm for this problem. And what we can show is that we can solve these problems for up to 10,000 features. If I want to give you some numbers, 10,000 features, this is just so the theta matrix is P by P, is 10,000 by 10,000. And because we are using L0 type methods, we have something in order of 50 million binary variables. And we are solving a problem with 50 million binary variables in like, I don't know, 100 seconds or something, 200 seconds. And it is faster than any polynomial time algorithm that we know by a factor of 10 or even more. And statistically, what we see is that generally we are doing the best. And in terms of support recovery also, we do very good. And if you want to see more how we do this, please come to our poster, field poster number 1. Thank you.
Okay. Can I have all of the slides since transition doesn't work? Yeah, another one. Thank you. OK. Hi, everyone. I'm Renato. Not a lot of time for greetings. And the work is about Gaussian processes at the Helmholtz, pun intended, because it's about like modeling ocean currents. And the idea is that we might all agree that it might be of interest to actually model ocean currents for many reasons and understand how things move in the ocean. For example, for forecasting oil-speed dispersion or understanding biological productivity. If we set this up in a statistical framework, what we have is that we have some freely floating buoys left in the ocean, and we measure the drifter traces, as you can see in the picture. And we are willing to model the spatial and temporal components of these, whose behavior is highly, highly nonlinear. More formally, we want to extrapolate a smooth function, which is the ocean flow, from some places where we observe it to some other places where we don't. And we are willing to do this with some measure of uncertainty. This should ring a bell, and the bell should be Gaussian process regression. The issue here is that it's not very clear how to actually do GP regression here, because we have to set the kernel and understand where to put the prior. If we do this in a naive way, that is by simply putting two independent priors on the two velocities components of the drifter traces, we end up with a model that is not able to predict the very physical properties of the ocean currents, for example, vorticity or continuity of these currents. And where our solution comes in, which is combining Gaussian processes with the Helmholtz decomposition, which is a decomposition particularly suited for the problem, because it decomposes a vector field into a vorticity and a divergence component. And by putting priors on the two components itself and using some properties of Gaussian processes, we are able to actually retrieve the physical properties of interest, and the computational time is just small constants more. And yeah, if you want to hear more, you'll find me outside at the poster. Thank you.
Hi, my name is Wenyu Chen. So I'm going to talk about a new computational framework for log-concave density estimation. So basically, we are interested in this like MLE problem, where P is log-concave density, which means that it's a density whose logarithm is concave. This is a central problem in the non-parametric shape constraint inference. And so right-hand side is a shape is an example of the shape of the log-concave density. So this Q et al. Shows that this problem can be actually reduced to a convex minimization problem with n variables phi I, where you can think of phi I as the negative log density at each data point xi. And so this problem is actually very hard to solve due to the second term, which is a non-smooth integral term. So our goal is to develop a scalable convex framework with computational guarantees. We have also our open source implementation available on GitHub. So basically here, in the second term, the non-smoothness will lead to a slow convergence rate, and the integral term will makes it hard to compute the value and subgradient of the objective function. So therefore, we propose to use some different smoothing techniques and discretization approaches to kind of makes this problem too easy to solve. And in practice, our numerical experiments show that our approach is actually 30 times faster than the current existing method. And we also provide some theory with computational guarantee, which is an improvement over on the direct application of existing theorem. So you can also see more information in this archive paper. Thank you very much.
Hi, my name is Tin Nguyen. My talk today is about Markov chain Monte Carlo. So Markov chain Monte Carlo is often used for clustering and similar tasks. But MCMC in practice is notoriously slow to run, and naive uses of parallelism to obtain more accurate estimates usually fail. In this work, we provide a fast that is accurate and also accurate to benefit from parallelism for MCMC and clustering. To expand upon this really briefly, we note that MCMC is used to do posterior expectations in probabilistic clustering models. Ideally, we would like to get really accurate results in little wall time, but the large bias in MCMC makes these two goals incompatible with each other. Even if you could run many short chains in parallel, you would still get really inaccurate results because IID sampling only reduces the variance and not the bias. Recently, Jacob et al. Have developed a framework to debias the short Markov chains using coupling arguments. At a high level, if you could simulate two chains until the values of the chains are exactly equal or they meet, then you could debias each chain. But existing work has not demonstrated couplings for partition valid models. Our contribution is first developing an efficient coupling for these partition models. We quantify distances in terms of partitions instead of label space to avoid the label switching problem. And we basically simulate the chains using optimal transport principles. Our numerical experiments show that if we have enough processors, then this coupled chains idea performs better than naive parallelism. The vertical axis is the percentage error with respect to some ground truth expectation. The red line is the error of a naive use of parallelism. We see that the error remains pretty flat, even if you increase the number of processors because of the bias. In blue is the error from our method, which is unbiased. So based on bias variance decomposition, the error will go to 0. Thank you.
Hi, I'm Raz. This talk is a teaser about our work for causal inference in sequential experiments that are being run for many sequential decision-making problems in mobile health and online education. And the setup we consider is you have n users that are sequentially treated for t time periods, and you're using policies that adapt over time. So these are policy that change with time. So at any given time, you randomize these end users, or you treat them with interventions drawn from policy pi t. Then, depending on the intervention or action assigned, you observe a noisy potential outcome corresponding to the treatment assigned. And then based on the data, you update your policy to pi t plus 1. And this kind of framework is, you use bandits or RL algorithms to update these policies in order to personalize or go towards personalization, as Shaoli was talking about. So in many applications, people run these trials. The kind of questions we are interested in is, with such trials, how can we do after-study inference? And the kind of questions we are interested in is, was there an average treatment effect? Was there a heterogeneity in treatment effect across users and time? The approach we take is slightly ambitious. We try to do counterfactual inference, meaning that we try to estimate all the missing data. So if you fix a treatment, say 1, the goal is to estimate all the missing outcomes for any user I at any time t for that corresponding treatment. And you can see that if you fix a treatment, it's a matrix completion problem, where the missingness has a special structure because of this sequential sampling. What we do is we propose a variant of nearest neighbors, which is like the relevant neighbors approach Shaoli was talking about. And we prove that that simple approach actually works under a general latent factor model. And the kind of results we show is, if you have bilinear latent factor model, we can show consistency for any user and actually any time during the study when n and t go to infinity. And for a stronger result, like a central limit theorem, we are able to show for a more general nonlinear f, but only at the end of the study. So only for the last time point, but again for a single user under suitable conditions that appropriately normalized estimate satisfies the CLT. Thank you.
So hi, my name is Sam El-Shayari. I'm my first year's PhD student at MIT RC. And today I will present my work with Professor Gamarnik on the density subgraph problems in dense Erdős-Rényi graphs. So in our setting, we consider a graph on n vertices. And for all possible edges, we associate random variables z, I, j. And we define the density of a subgraph of size k as the sum of all these random variables on the possible edges in the induced subgraph. And our goal is to establish tight asymptotic expansions on the density of the densest subgraphs of size k, when k is the power c of n. And we consider 3 settings. The first one, the distribution of the random variables is Bernoulli 1.5, which is the classical setting. And the second one, the distribution of the random variables is Gaussian with mean 1.5 and variance 1/4. And the last one, we consider a generalized, any type of distribution A. And we're able to establish in the Gaussian case very tight asymptotic expansions when k is n power of c, and c is between 0 and 2/3, when n goes to infinity. And we're also able to establish some weaker asymptotics in the regime c between 2/3 and 1. And we can also mimic the same proof in the Bernoulli case when c is less than 1/2. The second main result in our work is a university type result where we were able to link the expected value of the quantity of interest when the distribution is A to the expected value of the Gaussian case modulo an error term, asymptotic error term, provided some assumptions on the first moments of the distribution A. And one application of this work is that we're able to establish the existence of overlap gap property in the transit click recovery problem in the Bernoulli case when C is less than 1/2, which is an extension of a recent work on the subject. And if you want to discuss more on this work, please join me in the poster session. Thank you.
Hi, my name is Adam Fish, and I'm in CSAIL, and I work with Tommy Akala and Regina Barzilai. The subject of our work that we're presenting at the poster session is very relevant to what Professor Shaoli talked about in terms of how do you build trust with a calibrated model. So suppose we train a model, like let's say we're trying to predict the occurrence of breast cancer in a couple years from now. And so normally we would train some sort of neural network, and it would give us a prediction which would say, are we at risk or are we not at risk? And it would give us some associated confidence with that. But the problem is that if you're asking the questions like, confidence for me, or how sure are you of this confidence, is that we might be misled, essentially, if that confidence is not calibrated. However, if the confidence is calibrated, and we term calibration as the probability that the model is correct, given that its confidence level is p, actually equals p, so if your confidence level is 90%, then 90% of the time for predictions like that, you are correct. Then we term it to be calibrated. The problem is that this is hard to, even in distribution data, to guarantee, and especially when you go out of distribution to things that you haven't trained on the lab, you don't have a lot of data for, is you may not be calibrated. So there's an area of selective prediction where we can make a decision to either abstain or not abstain in order to make predictions, and we term a new kind of notion of calibration under selection according to the conditional probability, the probability that your model is correct, given that your confidence is p, and also given that your sample is selected. So we have some findings and some empirical results about how to improve the calibration under selection, and I'll be happy to talk about it in our poster session.
Hey everyone, today I'll talk about randomized control trials and matching algorithms. So matching algorithms are actually used all around the world to solve many practical problems. But just to fix ideas, let's think about a school choice setting where we have to match students to schools. Okay? In many of these school choice settings, you have researchers that run randomized control trials where they, for example, provide information about which are the good schools in the area, and then they measure the probability of admission into this good schools for the treatment group against the control group. Well, it turns out that difference is not a valid estimator for the average treatment effect of the treated, even if we have a randomized control trial, because the matching algorithms will break the stable unit treatment value assumption, also known as the no interference assumption. In fact, one can show that most of these empirical applications are overestimating the average treatment effect on the treated. So that's a problem. And the question is, how can we solve it? Well, in this paper, I provide a simulation-based non-parametric estimator, which is asymptotically normal, and it's a consistent estimator for the average treatment effect on treated. I also provide a few extensions. So if you are interested in knowing what would happen if you scaled up this treatment and gave more information to more kids, what would be the result? What would be your treatment effect? You can also do that, among other things. And I also provide an application on the Chilean school choice system. So in this setting, I show how when you compute the naive estimator and you compare it with the consistent estimator that I propose here, the differences can actually be quite sizable. So yeah, I'm happy to talk more about this, and I'll see you at the poster session.
All right, there's no pointer here. Hello, everyone. I'm going to talk about robust and monotonic neural networks. It's a novel kind of architecture. First, let me tell you about what it does. First, the architecture is robust to outliers in the sense that you have guarantees that there will be no changes above or below a certain scale, so no large changes if the scale changes very little. And this is due to the fact that the model is guaranteed to be Lipschitz continuous for some constant L. That's a relevant scale to the problem, so you can think of it as some sort of resolution or something. Second, it can be made monotonic in any subset of its features, and you can think of a million examples for which that's useful. So this is a toy problem where we know that the output of this neural network is supposed to be monotonic in a certain feature. And if you train your usual neural network architectures with enough capacity, then you can capture all the noise that you can see on the right. But if you train this novel architecture, then you have guarantees that it's going to be monotonic, which is something that's desirable. You can think of it as, I don't know, some sort of domain knowledge. The middle picture shows that this architecture can represent arbitrarily complex decision boundaries for classification problems, and this just means that it's an example for some kind of Lipschitz function. So this is a universal approximator of all Lipschitz continuous functions, and we can represent any function with that. Okay. Now let me tell you how it does it. So the robustness is achieved by constraining the operator 1 norm of the weight matrices of each layer. So you can think of it as some sort of module that you append to every linear layer that you have. it'll constrain the Lipschitz constant of the resulting network with respect to the infinity norm, and this choice is made such that the monotonicity part works. Of course, this requires activation functions which are which have gradient almost one everywhere, and this is why we use group sort. More details on that in the poster session. And finally, you can make the architecture monotonic in any subset of features by adding the simple residual connection at the end, where you see this linear term that's scaled by lambda, and this makes the output monotonic since the gradient in any direction is going to be non-negative. Yeah, more on that later.
Thank you for all joining. My name is Eren, final year PhD student working with David Gomarnik. And my poster will be on the symmetric binary perceptron and algorithmic hardness of this model. Let me tell a few things about the model. You take two parameters, kappa and alpha, positive, generate a number of IID Gaussian constraints xi, where alpha acts as the constraint density, and you look at the following random set of all binary sigma such that sigma satisfy the rectangular constraints with respect to xi's. This model has many motivations, including the early study of neural network models, random constraint satisfaction problems, and combinatorial discrepancy. It turns out this model has two conundrums. The first one is a statistical to computational gap. That is, as kappa tends to 0, the algorithms at which the solutions exist are much higher asymptotically the densities at which efficient algorithms can find solutions. And such gaps exist in many combinatorial or many statistical inference problems. A second one is this model exhibits an extreme clustering phenomenon, which is that for all positive densities, even in the easy regime, the solvable regime, typical solutions of this model are isolated singletons, and solution, the distance from one to another is order n in Hamming distance. So in our work, we borrow some insights from spin glass theory, establish an intricate geometric property called the overlap gap property, which informally states that the near optimal solutions of this model are either close or far, so no intermediate distance solutions. We show that this model exhibits a variant of this multi-overlap gap property for densities kappa square log 1 over kappa, which is short of a logarithmic factor. It matches up the algorithmic threshold. We rule out stable algorithms by leveraging this, using Ramsey theoretic arguments at the exact same threshold, which is an important class that captures algorithms such as AMP and low-degree polynomials. And we finally establish a known algorithm for this model is stable in our sense. Thank you. And I look forward to seeing you.
Hi all, my name is Siddharth. I'm a postdoc at IFI, that's the Institute for Artificial Intelligence and Fundamental Interactions here at MIT. And so it's common in many domains to describe observations using complex simulators. So that's the black box in the middle there. And it's often parameterized by some parameters on the left that we're interested in inferring. So the simulator actually encodes implicitly the likelihood associated with the model. And we can sample from this likelihood by just running the simulator in the forward direction from left to right on this slide. It's much more difficult to do inference in this setting, so to go from right to left, so for a given observation, infer the parameters that we're interested in. And that's just because to do this, we have to integrate over a potentially large latent space. So we have to marginalize over all possible paths that the simulator could have taken to arrive at our observation. So this is a general setting for a class of methods called likelihood-free inference. Likelihood-free is a bit of a misnomer because there is a likelihood. It's just implicit in the simulation rather than written down explicitly. So likelihood-free inference methods have seen a lot of development in the last few years, borrowing some of the advancements from differentiable programming or machine learning. My particular domain is particle astrophysics. So I use simulators to connect theories of new physics, like dark matter, to astrophysical observations. And in the particular application that I have the poster about, we proposed a likelihood-free inference pipeline to extract features from dark matter imprinting on observations of stars due to gravitational lensing. So the idea is we have dark matter in our galaxy, we have stars, and the dark matter will gravitationally lens the stars. And this is something that would happen on millions of stars. So this involved using a neural network that can efficiently extract features from the data, and then doing likelihood-free inference to get out likelihoods associated with the dark matter theory. And in this case, we can do, for example, robust uncertainty quantification and so on. Yeah, if you're interested, find me at the poster session. Thank you.
Hi, everybody. I'm Jonas, and this is joint work done with Curtis and Anish, and we're all ex-PhDs from CSAIL. And so in machine learning today, especially supervised learning, everybody operates under the assumption that labels are correct, and you're training your models to spit out these labels and measuring it according to its test accuracy. But actually, in many of even the most high-quality, well-known data sets, like MNIST, ImageNet, a lot of the labels are just plain wrong. So here we're showing some of the given labels in the top row, and then we've built some tools, a bunch of algorithms that we've open sourced in a tool called CleanLab that can automatically identify these label errors and correct them for you. And so we're actually building a team trying to do a lot of this open source development and research new algorithms in this space. So if you're interested, please reach out. And yeah, so we ran this tool on all the major machine learning benchmark data sets and found around 3% of the errors, labels are erroneous, I should say. And this spans really image data, audio data, text data. And we think this is a much bigger problem in, data in industry that are much less curated than these data sets that have been studied by thousands of people. And so you can check out labelerrors.com and browse through all the label errors for each of these famous data sets. We've curated them there. We've built some data-centric AI tools where the goal is really in data-centric AI to keep the model fixed and iterate on the data set to optimize the data to ensure you have the highest quality data rather than the highest quality model. And that seems to be a big trend nowadays for really getting much bigger accuracy boost than you would get by tweaking hyperparameters of your model. And yeah, as I mentioned, we're open sourcing all this, so please come by my poster if you're interested in learning more about the details of the algorithms.
Okay, hey everyone, my name is Adit Rada, and I'm here to talk about our work on constructing wide and deep neural networks that achieve optimality in classification. And so I think we all know that neural networks are extremely successful in practice, especially for this problem of object classification. But it's been a long-standing question of how can we actually construct neural network classifiers that achieve optimality. And what I mean by this is if you're given some training and test data, as you collect more and more training samples, you want your neural network to converge to this Bayes optimal classifier, which is the model that's kind of the best you can do if you had known the data distribution in advance. So prior work actually shows that such neural networks exist via this classical approximation results, but they don't really give a tractable or computationally feasible algorithm for finding these. So in this work, we actually construct these infinitely wide and deep neural networks that when you train with gradient descent give you optimality. And we use this connection between kernels and infinitely wide networks given by the neural tangent kernel to do this. And as an example of the dichotomy of the two problems of regression and classification, the models that we consider are terrible for regression. They predict 0 almost everywhere. But when you're doing classification, where only the sign of the prediction matters, you can actually get models that are really good and achieve optimality. And more generally, what we do is we establish this taxonomy of all of these models, and we show that depending on your choice of network activation function, these models only implement one of 3 well-known classifiers, 2 of which, the one nearest neighbor and majority vote, are not optimal. But the singular kernel classifiers that these things can implement, a subset of these achieve optimality. And the cool part is everything is very explicit. So you can give me an activation function. I can then tell you which class of model this falls into. And in particular, we identify activations that give you optimality. And so a major outcome is we finally have this constructive proof of when neural networks achieve optimality for classification. And for more details, please come see us at our poster.
Hello. It may come as a surprise to you that probabilistic and statistical tools have actually been used to support the development of democracies in the late 18th century. In fact, a philosopher and mathematician, the Marquis de Condorcet, created this framework in 1785, where you model democracy as a collection of agents and agents that vote on a binary issues. And one of the outcomes is assumed to be more optimal than the other. So in sum, this reduces voters to a set of classifiers that have some probability of making the good decision. What the Marquis de Condorcet observed is that if the average expertise of the average member of that group is above a half, then the probability that the group is correct tends to 1 as n goes to infinity. This follows from the law of large number. In turn, what this means is that the group here is more accurate than the most accurate of its members. And this has been seen by some revolutionaries as proof that crowds could be wise. Of course, if you revert the premise that the average expertise of the average member is greater than half, then the result is reverted and the crowd becomes quote unquote stupid. And in particular, the crowd becomes less accurate than the least accurate of its members. Fast forward in the 21st century, where we're trying to redesign, redistrict how institution looks like in democracy. We've seen many proposals between drawing citizens at random to put them in assemblies, do more referendums, and more recently a proposal came up to create what is called liquid democracy. Liquid democracy is a system where you can either vote directly or delegate your vote to a trusted peer. So let's assume that this is the group in this room today, and we have some here hidden ties that represent the way we are connected to one another. The idea is that if I need to vote on topic T, I can delegate my vote to someone, let's say Professor Gormanik, who in turn can delegate his vote to someone else, delegating as well my vote. And so this creates a delegation graph that we model through a stochastic process. We assume that I have many people I can delegate to, and for different issues, I will delegate to different people. The promise of liquid democracy is that it will enhance collective wisdom when it's there and trigger it when it's not there. And of course, intuitively, the idea is that if you delegate to people that are more expert than you can increase this probability that you're correct in the Condorcet setup. And this up to the moment where people actually concentrate too much power, in which case you have now a few people actually just concentrating power and creating the bad case I showed in the Condorcet setup. And so what we've been studying in the past years was trying to understand the kind of behaviors, the kind of human behaviors, delegating behaviors, such that for a given graph topology, liquid democracy achieve its promise of achieving greater collective intelligence. Thank you.
Hi everyone, my name is Enzo and my advisor is Yuri Poliansky. So here's what we have, n time series and also k observations for each of them. Now how are we going to predict the next value in each time series that minimizes this L1 loss? So one way, the baseline is to just predict the median of the observations for each time series, and this is the MLE of the Laplace distribution. But what if we also know that each time series is somewhat distributionally similar? So for here, what we do is that we model the parameters of the Laplace distribution as having a common prior distribution, which we name it as pi. But what is pi? Without assuming any underlying structure of pi, we would estimate pi as a non-parametric MLE, so which we name it as hat pi. So what we show is that under really mild conditions on the observations, hat pi is supported only on the observations themselves. So what this means is that it allows us to reduce the problem into finite dimension and just run convex optimization to get the hat pi. So after that, what we are left to do is to predict the next value based on our estimated prior and also the observations, which we will just predict the posterior median of this thing. Now, let's predict the log returns of the stocks exchange data set and also the exchange rate data set. So from the thousands of observations, we will partition these thousands of daily observations into small windows, each of size 5, and then run NPMLE plus empirical bias versus median on each of them. And what we have shown is that our NPMLE plus empirical bias is 10% better than the median estimator on average based on the L1 loss. So, and for more information, please see us at the poster session. Thank you.
So hello everyone. So my name is Hao Yue, and I'm a PhD student at ORC here at MIT. So my poster will be a topic on linear regression with mismatched data. So here we are going to study a model which is a simple variant of linear regression, in which here we have an additional parameter p star. This means that this model will probably see some mismatches between the interpreters and responses. And here, this parameter p star is an unknown permutation matrix corresponding to these possibly unknown mismatches. Here we are assuming that p star, the number of mismatches that is in p star is much less than the total number of samples in order for this model to be identifiable. And so our goal is to try to estimate both this p star and beta star from the observations x and y. This problem actually have a long history dating back to 1960s under the name of broken sample problem. It kind of regains some attention recently due to applications in various areas like linkage attack or multi-target tracking, etc. So what we're going to study is simply the least squares estimator. So here, we're treating both this parameter p and beta as variables that we want to optimize to decrease squared error. And this problem is actually hard to be solved to optimality because of the underlying combinatorial structure rooted in p. So what we are going to do is pretty simple. We are going to study a simple local search algorithm, which, informally speaking, it makes a swap in each step of the algorithm. And we will repeating this until it has reaches the local minimum. Although we don't know if this algorithm can solve to optimality, but we can actually show that under some reasonable assumptions of the model, we can actually show that a nearly parametric error bound for the estimator that we obtained. And we will also derive iteration complexity on the algorithm, that is number of iterations needed to compute such an estimator. So finally, we can present some numerical results showing good performance in running time or estimation accuracy compared to existing algorithms. So if you're interested in this topic, come join me at the poster session. Thanks.
Hey everyone, I'm Xin Yi, and I'm a graduate student at SDSCon in Leeds, working with Professor Ali Jababai. And I'm presenting our project of using higher order network information to improve overlapping community detection. So finding community structure is a fundamental problem in network science. However, one major challenge is that nodes often belong to multiple groups simultaneously, as shown in the left plot, where we have an ego view of a social network, and the central user sees its memberships as 4 different groups. On the other hand, links in the communities usually form for a single reason. Thus, link partitioning methods overcome this challenge of overlapping community by redefining communities as groups of links rather than nodes, and find overlapping community structure in a natural way. However, the problem is that current link partitioning methods is solely developed for graph representations of networks, which can only model pairwise relationships in the network by edges. Higher order information and interactions are common, crucial in many complex systems. For example, the right-hand side is a collaboration network. The existence of the triangle, meaning that 3 of us having co-authored a paper together, provides actual valuable information to study this network. So in order to incorporate the higher order information, we develop link partitioning methods on simplicial complexes, which is a higher order generalization of graphs. we use random walk defined according to the higher order Laplacian to perform the link partitioning. And we show that by using the random walk, and the random walk actually can be recast as a graph random walk on a leafy line graph transformation of the original simplex, simplicial complex as shown on the right-hand side. And we show that using the random walk and the one method is guaranteed to produce interpretable results on the original complex. Experimental evidence also suggests that by using the higher order information, we get substantial improvements in identifying the overlapping communities within the network. So if you would like to know more about this project, please join me at the poster section, and I'm happy to chat. Thank you.
Hi, my name is Leon, and today I'll be talking about my work on privacy-induced experimentation and causal inference. So differential privacy is an increasingly popular technique that adds noise to the underlying data so that no data from any specific individual is exposed. However, this technique has been increasingly criticized by many social scientists, especially pertaining to the 2020 census, as adding noise to the data could potentially influence many downstream use cases of the data. But what if we can use this data to our benefit, or this noise to our benefit? Causal inference methods rely on data from randomized experiments or non-deterministic policies. Under differential privacy, the noise that we add to the data turns any deterministic policy into a pseudo-experiment, so that any noisy units that would have been assigned to the treatment group without DP might now be assigned to the control group, or vice versa. So this noise can be used to estimate causal quantities. The main takeaway here is that we can characterize deterministic policies applied to differentially private data as corresponding to stochastic policies applied to the original private data. So this is the scenario that we have in mind. Under the trusted curator model, all the units would give their private data to some trusted curator. The curator would add some noise and then would enact some policy pi. The curator then wants to know what would have happened under an alternative policy pi prime. So to evaluate our models, we use data from the Census's American Community Survey, and we wish to know the effect of a specific provision from the Voting Rights Act on voter turnout. So in this case, every county in the US would give their private data to the census. The census would add some noise to it, and then would assign each county to whether they would translate their voting documents to Spanish or not based on some thresholds defined in the law. Because the curator has both the original private data and the distribution for where the noise came from, they can actually calculate the propensity score. So after they observe the voter turnout, they can then estimate the policy contrast between pi and pi prime. If you want to learn more about how we do this, please visit my poster.
Hi everyone, I'm Jackie, second-year PhD student working with Caroline Wooler. I'm here to present our poster, Matching a Desired Causal State via Shifting Inventions. So we're interested in this problem of transforming a causal system from an initial state to a desired state. For example, this is an abstraction of this real important problem in biology, which is known as cell reprogramming. In this problem, the biologist is interested in transforming, for example, cell type 1 into cell type 2, by manipulating the genes which are regulated by the underlying causal system known as the gene regulatory network. And this can be done by interventions, which are knockout interference or activations of genes. So in order to solve this problem, we first frame it into these causal matching problems, and then we show feasibility, which is that this problem exists a unique solution. Afterwards, we characterize what we can learn from the interventions by defining this shift interventional Markov equivalence cost. And then we propose two active learning strategies, which are optimal up to a log factor, which we also show in simulation is able to outperform several baselines. So if you would like to know more, please visit me at the poster section. Thank you.